Welcome to today's class on functional analysis. Today we discuss a theorem which is required in the proof of Hanbanach separation theorem. So theorem, let X be a normed space over K, E be a non-empty open convex subset of X, and Y be a subspace of X such that E intersection Y is empty. Then there is a closed hyperspace. Then there is a closed hyperspace Z in X. There is a closed hyperspace Z in X such that Y is contained in Z and E intersection Z equal to empty. Consequently, there is some F in X dual such that F of X is equal to 0 for every X in Y, but real part of F of X not equal to 0 for every X in E. Let X be a normed space over K, E be a non-empty open convex subset of X, and Y be a subspace of X such that E intersection Y is equal to phi. Then there is a closed hyperspace Z in X such that Y is contained in Z and E intersection Z is equal to phi. Consequently, there is some F in X dual such that F of X equal to 0 for every X in Y, but real part of F of X is not equal to 0 for every X in E. So proof. First we assume that K equal to R. Assume that K equal to R. We can use transfinite induction. In the form of Zorn's lemma. First we discuss what transfinite induction is. Transfinite induction. Let X together with the order less than or equal to be a non-empty well-ordered set. For each X in X, define Sx equal to set of all Y in X such that Y less than X. That is set of all predecessors of X. Suppose that a subset Y of X satisfies the property Sx and in Y implies X belongs to Y for any X in X. The principle of transfinite induction claims that Y equal to X. That is, if Y contains all predecessors of X, then Y contains X as well. Now we pass on to the proof of the theorem. Step 1. By Zorn's lemma, we prove the existence of Z. So that's the first step. By Zorn's lemma, we prove the existence of Z such that Y is contained in Z and E intersection Z is equal to empty. That is the first step. So by Zorn's lemma, we prove the existence of Z such that Y is contained in Z and E intersection Z is equal to phi. So that is step 1. So for which you let script W, family W, be a set of all W such that W is a subspace of X, Y contained in W, and E intersection W equal to phi. So by the hypothesis of the theorem, we have E satisfies this condition. Y is a subspace of X, Y is contained in Y, and E intersection Y is equal to empty by hypothesis. So by hypothesis, therefore by hypothesis, Y belongs to the family W. The inclusion W1 contained in W2 for W1, W2 in the family W define a partial order in family W. Every totally ordered subset of W has an upper bound in W, namely its union. Therefore, by Zorn's lemma, there is a maximal element Z in W. Then Z is a subspace of X, Y is contained in Z, and E intersection Z equal to phi. So this proves step 1. In step 2, we prove Z is a hyperspace, for which we prove if Z is not a hyperspace, then E intersection span Zx0 equal to phi, which will imply Z is not maximal. So to prove E intersection span Zx0 equal to phi, we prove the existence of such an x0. So we assume that Z is not a hyperspace. So suppose that Z is not a hyperspace, in X. So we shall show that there is some x0 in X with x0 does not belongs to Z, and E intersection span Zx0 equal to phi. So for which you consider S equal to Z plus union Re such that R greater than 0. Then S and minus S are open. in X. Since this is because since E is open, R is open. For every R greater than 0. And therefore, union RE such that R greater than 0 is open. Therefore, we can use 5.6a. Z is a subspace and union RE such that R greater than 0 is open. Therefore, Z plus union RE such that R greater than 0 is open. Therefore, by 5.6a, if so, it says 5.6a says if E1 is open in X, if E1 is open in X and E2 is contained in X, then E1 plus E2 is open. So letting E1 equal to union RE such that R greater than 0, which is open, and E2 equal to Z, we get S equal to Z plus union RE such that R greater than 0 is open. Finally, minus S is open. Now we prove three statements. Statement 1, S intersection minus S equal to phi. That is, S and minus S are disjoint. If not, that is, if there exists an element in S intersection minus S, there exists Y in S intersection minus S, then Y belongs to S and Y belongs to minus S. Now Y belongs to S implies Y equal to Z1 plus R1 X1, where Z1 belongs to Z, X1 belongs to E, and R1 is greater than 0. Y belongs to minus S implies Y equal to minus Z2 minus R2 X2, where Z2 belongs to Z, X2 belongs to E, and R2 greater than 0. Now, since Y belongs to S intersection minus S, we have Y is equal to Z1 plus R1 X1, that is equal to minus Z2 minus R2 X2. That is, Z1 plus R1 X1 equal to minus Z2 minus R2 X2. Therefore, R1 X1 plus R2 X2 This is equal to minus Z1 plus Z2. Now dividing by R1 plus R2, this is possible because R1 and R2 is positive. Therefore, R1x1 plus R2x2 divided by R1 plus R2 equal to minus Z1 plus Z2 divided by R1 plus R2. This belongs to E intersection Z. Since E is convex, R1 x1 plus R2 x2 divided by R1 plus R2 belongs to E, because x1 and x2 are elements in E and E is convex. Since Z is a subspace, minus Z1 plus Z2 divided by R1 plus R2 belongs to Z, since Z1 and Z2 are elements in Z and Z is a subspace. Therefore, LHS belongs to E, RHS belongs to Z. Therefore, LHS and RHS belongs to E intersection Z. Therefore, R1 x1 plus R2 x2 divided by R1 plus R2, that belongs to E, and this is equal to minus of Z1 plus Z2 divided by R1 plus R2. This belongs to Z. So this belongs to E intersection Z. But we have E intersection Z equal to phi. It is empty. But we are getting that E intersection Z is non-empty here. So that which is a contradiction. Therefore we get a contradiction. That is S intersection minus S equal to phi. We get a contradiction. This contradiction is due to our assumption that S intersection minus S is non-empty. Therefore, we have S intersection minus S is empty. Now we prove the second statement. 2. S union minus S is contained in Z complement. If S union minus S is contained in Z, so then there exists a Z2 in Z such that Z2 equal to plus or minus Z1 plus R1 x1 for some Z1 belongs to Z, R1 positive and x1 belongs to E. So this implies plus or minus Z2 equal to Z1 plus R1 x1. So this implies x1 equal to plus or minus Z2 minus Z1 divided by R1. This belongs to E intersection Z, since x1 belongs to E and Z2 minus Z1 plus or minus Z2 minus Z1 by R1 belongs to Z, since Z is a subspace, and x1 equal to plus or minus Z2 minus Z1 divided by R1, which is a contradiction, as E intersection Z is empty. This contradiction is due to our assumption that S union minus S is contained in Z. Therefore, S union minus S is contained in Z complement. The third statement is S and minus S are open in X. Which is already proved. Therefore, we have three statements. One, S intersection minus S is empty. 2, S union minus S is contained in Z complement. And the third statement is S and minus S are open in X. These three statements shows that S union minus S not equal to Z complement. Otherwise, that is, if S union minus S equal to Z complement, then Z complement is the disjoint union of two non-empty open sets S and minus S. That is, Z complement is not connected. Take it as statement star. But we have X is a normed space, and by assumption Z is not a hyperspace. Therefore, by lemma 7.2, Z complement is connected. Which is a contradiction to star. S union minus S equal to Z complement is not possible. Therefore, S union minus S is not equal to Z complement. There exists some X naught in X such that X naught does not belong to Z union S union minus S. Observe that if Z complement equal to S union minus S, this is not possible, since Z union Z complement equal to X. Therefore, if Z complement is equal to S union minus S, we cannot find an X naught in X such that X naught does not belongs to Z union S union minus S. So we claim that E intersection span Z X naught equal to 5. So we can suppose not. E intersection span ZX naught is not equal to 5. So consider an element in E intersection span ZX naught. So let X belongs to E intersection span ZX naught. That is, X is equal to Z plus Tx naught for some Z belongs to Z and T belongs to R. T equal to 0 implies X equal to Z. So this belongs to E intersection Z. X belongs to E and Z belongs to Z. So X equal to Z means there exists an element in E intersection Z, which is a contradiction since E intersection Z is empty. Now suppose that T is greater than 0. So if T is greater than 0, then X naught equal to X minus Z divided by T, or this is equal to X by T minus Z by T. This belongs to S. This is because since S is Z union RE such that R is positive. So here minus Z by T belongs to Z, X by T belongs to RE. So which is a contradiction since X naught does not belong to S. Because X naught is not an element in Z union S union minus Z. Now T is less than 0 implies X naught equal to again X by T minus Z by T. This belongs to minus S since T is less than 0, which is a contradiction since X naught does not belongs to minus S. Therefore, X does not belongs to E intersection span ZX naught. Therefore, X cannot belong to E intersection span ZX naught. Therefore, E intersection span ZX naught is empty. Thus, the span ZX naught is an element in the family W. It is strictly larger than Z, contradicting the maximality of Z in family W. Therefore, Z is a hyperspace in X. This proves step 2. So we prove the remaining part. Since E is a non-empty open set in X and E intersection Z is equal to phi, it follows that the closure, set closure of Z cannot be equal to X. We have Z is contained in set closure, that is contained in X, and Z is a hyperspace. Set closure equal to Z, that is Z is closed. We have by 2.5b, if X is a non-zero linear space and if Z is a hyperspace in X, then there is a linear functional f on X such that Z equal to 0 space of F. We have X is a non-zero linear space and Z is a hyperspace. Therefore, there exists a functional f from X to R such that 0 space of F equal to Z. Now, X belongs to Y implies X belongs to Z, since Y is contained in Z. Now, since Y is contained in Z, X belongs to Y implies X belongs to Z. And we have Z is equal to 0 space F, 0 space of F. So this implies X belongs to 0 space of F. So this implies f of X is equal to 0. If X belongs to E, then X does not belongs to Z, since E intersection Z is empty. Therefore, f of X is not equal to 0 because 0 space of F is Z, since 0 space of F is Z. By 6.4, we have F is continuous if and only if 0 space of F is closed. In X. Since 0 space of F is Z and Z is closed, F is continuous. Thus, the theorem is proved for K equal to R. Now we prove the theorem for K equal to C. So let K equal to C. Regarding X as a linear space over R, we find continuous real functional U from X to R. such that u of x equal to 0 for every x in y, and u of x is not equal to 0 for every x in e. By what we have proved. So as in lemma 7.1, let f of x equal to u of x minus I u of ix for x in x, so that f from x to c is a complex linear functional, and clearly f is continuous. Now let x belongs to y. So this implies ix belongs to iy, iy is equal to y. Hence, f of x is equal to u of x minus I u of ix. Since x belongs to y and ix belongs to y, u of x is equal to 0 and u of ix is equal to 0. But thus, this is equal to 0 minus I into 0. So this is equal to 0. Since x belongs to y and ix belongs to y. Also, x belongs to E implies u of x is not equal to 0. Therefore, a real part of f of x, which is equal to u of x, that is not equal to 0. Therefore, by 2.5a, since f is linear functional on x and f not equal to 0, set of f is a hyperspace in x. Since f is continuous, by 6.4, set of f is closed. Therefore, set of f is a closed hyperspace in the linear space over C such that y is contained in Z and E intersection Z is empty. So this proves the theorem. The preceding result shows that if y is a proper closed subspace of x, then there is some non-zero f in x12 such that f restricted to y is 0. In particular, if x not equal to singleton 0, then letting y equal to singleton 0, we obtain x dual not equal to singleton 0. So that's all for the day.